Let's talk about Chebychev's theorem for a few minutes. Basically, Chebychev's theorem tells us a bound for what percentage of observations should fall within a certain number of standard deviations from the mean, where the number of standard deviations has to be bigger than 1. Okay, and the nice thing about Chebychev's theorem is it works for any type of distribution. We have the empirical rule that only works for bell-shaped normal distributions, but Chebychev's theorem works for all distributions. So let's see what we have here. The average monthly mortgage payment in a large city is $1,850 with a standard deviation of $125. Use Chebychev's theorem to address the following questions. Round solutions to 2 decimal places if necessary. Okay, so the first question asks us 88.89% of the monthly mortgage payments need to lie between what two dollar figures? And then the next question, at least what percentage of the monthly mortgage payments lie between $975 and $2,725? Let us tackle them in this order. Let's do the second question first, since I think that might be a little better for explanation-wise. So let's see. At least what percentage of monthly mortgage payments lie between $975 and $2,725? So let me see if I can get a quick distribution drawn here. Give me just a sec. So we have something. I'm gonna draw a purposely not bell-shaped distribution. So maybe I'm gonna make it really skewed. What would mortgage payments look like? It'd probably actually be more bell-shaped, but here, let me just make a skewed distribution. In fact, just a quick review, what kind of skewness would that have? That would have a left skew because the tail of the distribution, the longer tail is on the left side. So this would be a left skewed distribution. Okay? So let's say the mean is just somewhere here, kind of towards the middle. I mean, since you have the bulk of the data over here, where the graph is tall, that's where the bulk of the data are. The mean would be further to the right. It wouldn't be exactly in the center, so maybe like right there. So that's the mean, let's just say for sake of argument, and the mean is 1850. So 1850 goes right there. Now, we want to figure out what percentage of the monthly mortgage payments lie between $975 and $2,725. So basically, $2,725 is over here somewhere. So I'm just going to label it 2725, and then 975 should be over here somewhere. In the way I set this problem up, these two numbers should be equidistant from 1850. That is, this distance right here should be the same as this distance right here when I set the problem up. Okay? Now, the question is, how many standard deviations are we talking about? So we're told that sigma equals 125. So there we are. Sigma is 125. That's our standard deviation. And basically the crux of this problem is figuring out how many standard deviations does it take to get from 1850 to 2725. Or you can ask yourself the similar question, how many standard deviations does it take for you to get from 975 to 1850? Okay, it's the same. This should be the same number of standard deviations from the way I said the problem. Okay, so let's think about this. Let's grab our calculator. So we have 1850 as the mean. How many times do I have to add a standard deviation, 125, to get to 2725? Let's see. So if I add 125, there's one standard deviation. Well, clearly we're not there yet. Let's add another standard deviation. So we've added now 2 standard deviations. Nope, we're not there yet. Add 3 standard deviations. There's a third one. Nope. Add a 4th standard deviation. Still not there. Add a 5th standard deviation. Still not there yet. At a 6th standard deviation. Nope, still not there yet. At a 7th standard deviation. And there you go. It took 7 times we had to add 125. That is we had to add a standard deviation 7 times to get from 1850 to 2725. So this distance right here, in terms of standard deviations, we'll just call it 7 sigma for 7 standard deviations. Now, just to check ourselves, this distance here should be exactly the same. Now, I know when I drew it, it's not exactly equidistant, but it should be. You know, my picture's not perfect here. So just to verify, let's do 975, and let's see how many times do I have to add 125 to get to 1850. Now, here's one way to think about it. Add, let's see if 7 does the trick. 125 times 7. If 7 is the correct number of standard deviations, this calculation should give us 1850. And it does. So yes, this distance right here is 7 standard deviations as well. And that's the crux, that's the information we need to answer the question. Because once we know how many standard deviations we're talking about, Chebychev's theorem says that 1 minus 1 over k squared times 100% of the data should be within k standard deviations of the mean. So at least this percent of data lies within k standard deviations of the mean. If I could write, that would be nice. There we go. Okay, so all we have to do is now plug in. So let's see. What we need to calculate is simply 1 minus 1 over 7 squared times 100%. And what do we get? Well, 1 minus 1 divided by 7 squared is 49. So 49 times 100 to convert that decimal to a percent. And we're supposed to round our answers to 2 places. So we're going to say 97.96%. Okay, so that's the at least 97.96% of the data lies between $975 and $2,725. Okay, now let's do the third question. The third question just takes it one step further. Instead of asking for a, oh, never mind, same question. It's the exact same question. Sorry, I was getting ahead of myself. So the third question is actually the exact same, except the lower value and the greater value, the upper and lower bound, let's say, are different. So we need to just repeat the process. So let me draw a different distribution there. Let's do this one maybe purple or blue, whatever this is. Let's see here. Yeah, so let's just do a different distribution again. Here, I'll kind of try to draw it the same, a left skewed distribution. And the mean is still the same, 1850, right there, kind of close to the middle, but more to the right. And this time, we're between 1600. So again, these are not drawn to scale, just 1600 is somewhere over here to the left, and 2100 is over here to the right. And the idea is how many standard deviations is that distance, which should be the number of standard deviations that is that distance. And so we repeat the same process. How many times do I have to add 125 to get from 1850 to 2100? So add it once. Okay. Let's add it again. Plus 125. There we go. Looks like it was 2 standard deviations. So we'll say 2 sigma for 2 standard deviations. And let's verify that using this left-hand side. 1600 plus 125. There's 1 standard deviation plus another standard deviation. 1850. Yeah, so we got to the mean. So again, the distance we're talking about is 2 sigma. And now we just need to plug into Chebychev's theorem. So again, here's our formula. So we say 1 minus 1 over 2 squared times 100%. Well, let's see, we can actually do this in our head. 1/4, 2 squared is 4, so 1/4 is this fraction, or 1 minus 1/4 is 3/4. 3/4 is 0.75 in decimal form times 100%. So no rounding required there, 75%. So 75% is the amount of data between here. Like if I shaded this, it would be at least 75% of the data. I didn't shade over here, but over here it would be at least, oh, wrong color. At least we said what, 97.96. All these data would be at least that. Okay. Now I saved the first part for last because this is kind of reversing the process. Reversing the process is saying, hey, at least 88.89% of the monthly mortgage payments lie between what 2 figures? So we're doing the opposite. So instead of finding a percent related to an upper and lower bound, here we are given the percent and we want to reverse engineer that upper and lower bound. So so a similar question might be, at least 97.96% of the data lie between what and what? Well, they lie between 975 and 2,725. So what should we do? Basically, we need to figure out what value of K gets you an 88.989%. That is, what value do you plug in to 1 minus 1 over K squared times 100%? What value do you plug in and you get 88.89? So that's the question. Well, let's think about it. We can just try a couple. Remember, for this question, I'm sticking to K being whole values. Technically, K can be fractions, but we know it has to be bigger than 1. We know it's not 2 because 2 standard deviations gave you 75%. We know it's not 7 standard deviations because 7 standard deviations gave you 97%. 88.89 lies between 97 and 75, so it has to be a number between 2 and 7. So let's just try the next whole number is 3. So if we plug in 3 in here, we get 1 minus 1 divided by 3 squared, that's 9, times 100. And what do you see? It gives you 88.89. So we got lucky here that 3 worked. But try 3, 4, 5, 6, 7, 8, 9, 10 until you get one that works. Okay, so we know that we're talking about 3 standard deviations. So K equals 3. Now, it's not our answer, but that will get us our answer. Because that means we need to draw a distribution. So 1850 is right there. 1850. And we need to go 3 standard deviations to the right and 3 standard deviations to the left because k equals 3. So this amount of shaded data here in the middle is at least 88.89. And let's see, what is 3 standard deviations above 1850? So 1850 plus 1 standard deviation plus 2 standard deviations. Oh, well, I guess I could do that. So there is plus 2 standard deviations. There is plus 3 standard deviations. So this upper bound is 2,225. Now, how do you get the lower one? You subtract 125 3 times. So 1850 minus, now you could do minus 125, minus 125, minus 125, but that's the same thing as minus 125 times 3 gives you 1475. So, we know that 88.89, at least 88.89% of the mortgage payments should lie between 1475 and $2,225. So the first question reverses the process that we did in questions 2 and 3. If you need any more help, just let me know.